thread online. Okay, we have come through our chapter 2. So to chapter 2, we will go through a few theory on the CFD solution procedure. So we'll look at, in general step, what is happening in the program itself. And then in the later session, we will complement what we learned using ANSYS Workbench later on. Okay, so the word CFD itself stands for Computational Fluid Dynamics. And the definition for CFD by the textbook is what you see on the screen. Basically, there are some keywords there. So CFD actually is a tools that we use to analyze engineering problems. Okay, so and it's a software that able to generate illustration like our video camera, that what happened inside or outside the structure or the body under a certain loading. Okay, so we investigate, we use CFD as a software, as a tools to investigate the cause and effect. The cause and effect. So what happened when we load like 10 kilogram on a fluid, or on a pressure 10 kilopascal on a pressure on a fluid? What happened? Will it move or will it deform, and so on? And also we can use CFD to look at the effect of heat transfer and mass transfer. Okay, so basically when people or when your junior asks you what is CFD means to you, so it's basically it's a tools, it's an engineering tools for us to investigate the cause and effect on the fluid dynamics. Okay, so it can also do heat transfer and mass transfer. But initially, the software was created to investigate the cause and effect on the fluid itself. So on the screen here, you will see these are the example that we can see in nowadays simulation. Of course, like 20 years ago or 30 years ago, even 50 years ago, everything was in black and white and the computer power is very low. But nowadays we have a very powerful computer, then we can do a lot of colorful presentation. Okay, so on the left here is an example of fluid dynamics, where later we will hands-on, we'll see the effect. And then the middle one is on the heat transfer, where you will see when what happens when you have a cool water go inside a chamber, and then there's a heat exchange in the beaker. Then on the right hand side, this one is a mass transfer. A simple illustration here is the nozzle, where when the mass travel from the left, and then when it enter into a divergent, a convergent section here, then something happened to the mass there. Density will change. Okay, so fluid dynamics information can be derived or can be divided into two main categories. We call it scientific first category. Another one is engineering. Scientific fluid dynamics information, it responds to heat and fluid flow. So it focuses on the structure of heat and fluid flow. Okay. One of the advanced CFD simulation will be on flow separation. You see vortex shieldings and all this. Right. Then for engineering, it will be on you set the loading, important engineering parameter, the boundary layer, and the application of loading, and so on. Yeah. So we have two kinds of, in CFD, we have two kinds of fluid, under fluid simulation. When you want to look at fluid dynamics information, we have two kinds. One is scientific, one is engineering. Okay. Yeah. So engineering is more on the loading created on the surface, for example, lift force, drag force, pressure, and so on. Yeah. So yeah, but nowadays the CFD software that we use, it already incorporated these two already. You can do very complex simulation solution. Okay, and this is example of a heatsink where in the middle on the screen here you will see that there is a plate here, aluminum plate, and in simulation, when someone use CFD to simulate, then you will have some parameter to set, for example, the heat flow from the left here from your electronic devices, or your heat source will go into this aluminum plate as your heat sink to disperse or dispense the, the very high energy on the left here. Then you have some constraint on the right here where it's insulated, where there's no heat that can go through to the right here. And we inside the heat sink here, we have a water inside here. So there's a conversion of energy from the left to right. And there's some parameter you can set in the CFD itself. For example, the length, the quantity of heat or energy that go into the system, the temperature that you want to set. All this is a parameter we set, and then we use a certain equation that we pre-program in the CFD, and then the tools itself, the CFD itself, help us to solve by using all the parameter that we input into the software. So later on, we'll input all this into ANSYS, and you will see what happened to the system itself. So these are the equation that we use when we come to heat transfer. So it involves some system, involves some parameter input, and then we see the cause and effect. What happened when we have input some heat from the left? What happened to the system? That is a cause and effect. And then the tools itself, they solve a few equations. For example, on the screen here, we show that there's a three equation there. So it will try to meet the requirement of the equation or some physics law or thermal law or energy law that you fix into the system. Then it generates the answer for you. So we are lucky that we have all the superpower, high power computer nowadays. So you try to imagine like 30 years ago before supercomputer come into the market, all the scientists, they have to use a lot of paper or even whiteboard to write the equation and try to solve. But nowadays we are lucky we have all these convenient tools. So this is an example for heatsink. And then this slide show you the results that able to generate from CFD. So this experiment done by Incorporo and David in 1996. So this one, that year is around the year where Windows was launched, Microsoft was started. So it's a computer era. So by that era, people can use CFD, can program a software, and it was named as a CFD to generate graphical data. For example, the one that you see on the screen here. Yeah. So you can see the changes, the cause and effect at a certain time. For example, on the screen here, you'll see time at 2.5, 5 seconds, and even 20 seconds. And you will see the graph generated by all the calculation in the graph form. In earlier computer, there's no print or present function. They use the word plot, P-L-O-T, plot. So they try to plot the value on a simple graph like that. Okay. And early 1996, most of the simulation, they run in a two-dimensional analysis. Okay, because the computer power is not that strong like today. Okay, so this example of heat conduction. Okay, another one is a flow simulation. For example, this is a system in the river. So on the screen here, you see a rectangular means is a control volume here. And you have a, in the middle here, you have a black dot. It means it's a pillar. You imagine there's a bridge and with a leg there, with a pillar there. So there's a pillar in the middle of the river. So, and then you input your flow speed velocity here. On the left, the water flow from the left to right, and then you use the equation that you learn in fluid mechanics. For example, to find the lift, drag coefficient, and all this, you input into the software itself, you program, and then you input the data there, and then you set the parameter, for example, the length from the boundary layer, and so on. And then you ask the computer to solve the equation for you. Yeah. So CFD itself is a calculator. So it helps you to solve the answer, to find the drag and lift coefficient for in this case. Yeah, in this case. So fluid dynamics can be generated by CFD itself. For example, on the screen here, you will see the result generated by CFD. And again, this is done by in 1990s. So you will see that everything is in 2D, but in that time it's so advanced. It's a very advanced technology already. Okay, and nowadays it's a very common practice. So you will see the first presentation from A1, B1, C1, D1. This one represent the vector. You will see maybe it's a black color, but on your screen you will see if you compare these four diagrams, you will see the changes of vector is there. Yeah, the changes of vector behind the pillar here. Behind the pillar, this black dot here. So you will see the change of velocity vector here. What happened here? Yeah. So another one is example. This one is example. This one is a pressure contour. Just now is a velocity contour. Yeah. This is a pressure contour. So CFD will help you to see the pressure contour when you input a certain value into the boundary layer or into the system. So later on in our hands-on session, we will also investigate the cause and effect. We will also investigate the velocity profile and also pressure profile later on. Yeah. So, and this is a graph form. Yeah, it's a graph form that also able to generate by CFD by using the formula inside. So basically, we need to always check whether our answer is correct or not, because the computer is just a calculator. So whatever you input, it will just calculate for you. It will not tell you what is right, what is wrong. Yeah. So we need to be careful when we come to CFD. The full control still on human. Yeah. Another textbook definition that you always see when you come to CFD is computational domain. Right, computation domain is the area or volume that area that we try to calculate. Yeah, so it will related to boundary condition, right, that you set. The next one is to answer the question how you get all this color, right? For example, on the screen here, you will see there is a tone of color for the pressure. So how the computer generate all these changes of color? You will see red color, blue color, and it represents some value there. So how the CFD do? So we as a user, we need to have some fundamental understanding. The CFD software is use a method based on the color, and the keyword here is discrete point. It uses something called discrete point in the calculation. It gives some score to your answer, and then it change or it convert the grid point, right, into color into color code. Yeah. So for example, 4,000, the value of 4,000, the CFD will calculate a grid point. It will come out a number. So let's say you get 100 kilopascal. So the computer will come out with 1,000 kilopascal equal to so many grid points. For example, 10 kilopascal equal to, for example, 3,023,2250 grid point for that 10 kilopascal or 100 pascal. Then the computer will register this grid point as a certain color. So it will go to the color board and choose based on the grid point. So it like you play with the color board. So and then you do a linear scale to get the color. So on the slide here, you will see some numbers. For example, 4,000 for a certain temperature, 4,000 maybe for 300 Kelvin, and 60,000 grid point for a certain viscosity value or vector value. Yeah. So at least as a CFD user, when people ask you, how do you know that how the computer or how the software get the color? How do you know that the blue color represent, for example, 100 kilopascal? Yeah, you can read from the graph itself. Yeah, but the background you should have some understanding there. So the computer generate the color is based on a technical term called grid point, and this grid point calculated from the equation that you input inside there. Yeah. So when you get the wrong presentation means something you input wrongly in the computer that generate the wrong grid point or grid score for the value. And when it comes to unsteady problems, steady problem means, for example, steady problem when you have a flow that flow with a velocity, constant velocity. When we have a constant velocity, you don't have acceleration. So when you don't have acceleration, when you apply second Newton law, F equal to ma, your velocity, your acceleration will become zero. Yeah. So when you analyze a non-steady or unsteady problem, meaning the acceleration is not zero, the rate of change of velocity is not zero, then you don't have you have unsteady problems. All right. And there are some mathematic name, a model name is called PDE, partial differential equation. So this one you learn in your calculus or advanced calculus, or even calculus 2. In the following slides, I will not type up the whole name. I will just use PDE, yeah, partial differential equation. This one is very famous for CFD, especially when we want to investigate fluid dynamics problems and heat transfer problems. Yeah. So in later on, chapter 3 onwards, you will see a lot of mathematical model come up, and all these fall under partial differential equation. Yeah. Yeah. So there's some characteristic for partial differential equation, where there are independent variables and spatial and temporal coordinates. So this one may be new to you. Maybe you don't know what is partial temporal coordinate. We will come into a certain chapter where we will discuss what mean by spatial, partial, and temporal coordinate. Yeah? But today, at least in your learning, there's one word called partial differential equation, and you know that in CFD, it is using partial differential equation to solve problems. Okay, so these are the basic understanding. When you use a CFD, a software, you should know that what is the fundamental or what kind of equation that you're using, right? So it falls under partial differential equation. Yeah? So we come to CFD. According to this textbook, it summarized the CFD into three stage. First is development of the software. Second, it talk about application, and then how we analyze the results. Okay, so we will look into development, and then we look at application, and then we look at analysis results. Okay, so of course, development, we'll go through these 5 steps. Okay? In development, in all the CFD software, you will go through these 5 general steps. First one, you will generate grid generation. In nowadays or end system, it's called pre-mesh. Discretization method is under mesh. So grid generation and discretization, nowadays ANSYS combine these two, it become meshing. It become a meshing process. All right. But in earlier CFD development, it start with the grid generation, means when you have a structure, for example, you have a plate, a blank plate here. So it will start with grid. It will start with drawing grid like that. Then it will break this small little bricks into smaller element, right? Smaller element. So you will have it can be 2 node, it can be 3 node, it can be more than 3 node, maybe 4 to 5 node. It become polygon shape, and then it become 3-dimensional. Okay, tetrahedral shape in 3D, and so on. So nowadays, ANSYS or other software, they combine these 2 functions into 1 section. Okay, so in your understanding, you should know that it start with grid generation, then it run the algorithm for discretization. So there's an algorithm mathematical model to run discretization, right? So there's a subject in advanced mathematics itself that call discretization, data discretization. So, however, for this module, we only touch and go. Yeah, we do not go very deep in the derivation, yeah, right? But we just apply what already been published. Then you go to a solution. Means you will go step by steps. You will look for the formula. Then after that, you will compute with the parameter. Testing is a solution. So you are testing, and you will in the background, you will test the acceptance, accuracy of the data, and then it present the data to you. Okay, so in ANSYS, you will see the word converge. Yeah? Later in second session, I will explain more about convergence or converge. So it's fall under testing. Yeah. So in general, we have 5 main steps: grid generation, discretization, solution, computation, and testing. So we have 5 steps in the software development of CFD. So this is the chart that you can see also in your hands out. So this one is so I think no, this one I do not include in the handout, but you can read from my PowerPoint slide later on. Yeah, so this is just a pocket my map for you. So in CFD development, yeah, there's lots of wording, don't worry, but you just follow the arrow. You just follow the arrow on the screen. So the first one is grid generation. We call it preprocessor stage, and the rest you can read. Second is followed by discretization method, and the rest you can read. Third one is solution methodology, which is a solver stage. The rest also you can read from the screen. And compute compute is a post process, right? Also, you can read from the slides, and testing is on the validation and verification. So this is a mind map when you come to CFD software. Okay, so later on you can go back to the slide and have a further look into it. So in grid generation, again, grid generation is discretization, means you break into big pieces into small pieces. Yeah. So on the screen here, you see there's a meshing process. So in ANSYS, again, in ANSYS, we call it mesh process. In textbook or in mathematics process, you cannot find mesh, but you can find discretization. So discretization actually is the same meaning for meshing nowadays. Right? The word mesh I think it just created like recently. So you cannot find the word meshing in the old textbook. Yeah. So later on, we will see what is discretization in ANSYS. So basically, the idea of discretization, again, in short or in a more simpler meaning, it just means you break a large piece of domain into a small domain. All right. A textbook is called discrete point. And then if you are running using a control volume equation, then you will call cell. So point, when you combine all the discrete point, it will become a cell. So on the screen here, I just draw a non-systematic cell. You have triangular cell. You have a tetrahedral cell in 3D. So all these are called cell. This example of grid generation, again, this is a very basic theory. You imagine that you have a plate again. This example is on a two-dimensional heat conduction on a square plate here. So before you start the simulation, when you want to start generating results, you start with the grid generation or discretization. So you break the square plate into a few small square here, and you input all the boundaries point and the parameter, what is on the left, what is on the right, what come in, what come out, and so on. Yeah, and you know that in early mathematics we have a vector form. For example, if the energy go to the x direction, they always like to use I. If the energy go to y, the calculation will use j hat, and to z they will use k hat, and so on. Yeah. So nowadays the computer will also use all these vector solution and generate result in the background. Okay. So in the shape generation or geometry, at the preprocessor stage, the computer itself will categorize it into two kinds of problems based on geometry. Based on geometry. So you have simple geometry problems and complex geometry problems. Okay. So in some of the software, you can select whether you want to simplify the calculation by using simple geometric approach or complex geometric approach. Yeah. So there are some options for you to choose. So what happens when you come to simple geometric problems? Yeah. So how do we know it is a simple geometric problems? When all your boundaries of computation domain, it referring to Cartesian, cylindrical, and spherical. Cartesian, it means that you have x and y axis, and you can label a certain point on xy coordinate, right? Cylindrical means you are on a certain point with the r and theta from a certain axis. Yeah. So you have X, Y, and Z. So here your coordinate of this point, for example, A will be in the term of R and theta. Theta is in radian. So this is the cylindrical coordinate system. Spherical, then you will have spherical and cylindrical quite similar, where you will use the theta term to define the location. Yeah. What happened in complex? So complex, it means that when your object or your domain do not calculate according to the Cartesian. I give you an example. On the screen here, for example, you have a square plate here where with a hole in the middle. And in here, when you generate grid, all the points are aligned to a proper X and Y coordinate. This is fall under Cartesian system. So even you have this kind of grid system, it fall below simple geometric problems. This is a simple geometric problems. Yeah. How you know or how you define is a simple geometric problems. It is because you can see that the shape is all is square, and you know that in Cartesian everything is in square. In Cartesian, you can define everything in square area and so on. Yeah. So this PowerPoint slide or these slides that you see on the screen, it tells you to differentiate what is simple geometric and complex geometry. Yeah. So this is the reason why is important to know whether it's a simple geometric problems. Yeah. Yeah. So the reason is that you see on the screen here that all the boundaries are aligned along the Cartesian coordinate direction, meaning you see all the boundary condition, you can align or match to the X and Y coordinate. I'll give you another example. The same simulation. The first one is on a square and a square hole. The second one, you have a square plate, but you have a circle, a hollow in the middle. So what you see on the screen here, this is a complex geometric problems. So where you can see that all the lines here is not able to properly align to the X and Y coordinate. And the dot here, you need to define using a very complex derivation. And you see the hole here, the middle of the hole here, you are not able to properly, because in the circle, in simulation, is using a line to join the point. So the process to convert a smooth curve into this shape, it will take some mathematics conversion. And also the coordinate of a certain point do not align to the Cartesian plane or cylindrical plane or spherical plane. Okay. So the special procedure to handle this kind of complex geometry is called curvilinear grid. Yeah, curvilinear grid process. So remember, sometimes why there's error in your calculation or in your software, it is because you choose the wrong approach. Yeah? So this is the curvilinear grid example. So we have two geometry problems, simple and complex. One is how you know that it's a simple. It is when it's simple means that you can align the boundaries with Cartesian, cylindrical, and spherical. If you cannot, then it becomes a complex geometric problems. All right. Any questions so far, Pratibha?
No, sir.
Everything okay for you?
Yes, okay, sir.
Okay, good. So far about the simple and complex. And yeah, now we look at a little bit on the discretization method or the PDE, partial differential equation, and also boundary condition, BC. Then how did it convert into a linear equation or linear algebra equation? Yeah. So LAE stand for linear algebra equation. BC stand for boundary condition. PDE stand for partial differential equation. So now we look at discretization or meshing method. Yeah. So in short, it just means that you are solving calculus problems into a simple algebra problems. Yeah. So this is what a discretization method do. There are three methods used in the meshing or in the discretization method. These three. So if you go and look for simulation, you look for CFD handbook, these three um, methods is famous, or can say it's a core algorithm that used in the software. The first is FDM, finite difference. Second one is finite volume. The third one is finite element. So later on in ANSYS, when you use, you know that you can run different simulation. You can run on the structure, you can run on the thermal, you can run on the fluid, and so on. So each type of the problem, you need to use different either one of these. Yeah. So the first one, finite difference, finite volume, and finite element. How do we know which one go which one? All right. So the first two, FDM, finite difference method, and finite volume, is solved for complex geometry problems. So both solve for this complex geometry problem. However, finite volume generate a better accurate answer. So that's why later on when you go and simulate fluid dynamics problems, in ANSYS itself, you can choose which method to use. Right? Most of the time by default, it will the dot or the selection button will fall on the finite volume method. So of course you can change it to finite difference method and so on. But in general idea, when you use ANSYS to simulate fluid, especially it involve volume change or mass change, then most of the time the algorithm behind is under finite volume method, and finite volume method again is for discretization. Finite volume method is used for meshing. That's why a finite volume method is to cut a very big pieces of object into small pieces. And finite element method is for mechanical, for solid material. Okay. Commonly FEM is for structural analysis. Means something is solid. So if not solid, is movable like fluid, then it fall under the above two method, finite difference or finite volume. Both give you answer. However, finite volume method give you better calculation time, means shorter calculation time, and better closer to the real number or real value. Okay, so again, when people ask you what is the formula or algorithm used in meshing, these are the three methods that used in meshing. Okay, so the first one, finite difference, finite volume, and finite element. Yeah. So again, finite element only most of the time it was used for structural analysis or something on the solid body. Yeah. This is example what happened inside the finite volume method. All right, this one you can read through. It means that there's a cycle how the finite volume method changed the PDE into linear equation, a partial differential equation, how it changed into linear equation. Yeah, so this is a simplified diagram. Of course, when you dig in later on, you will see a lot of complex equation come in. This is a simplified diagram. And in later chapter 2, later on, chapter 3 later on, then you will see equation like mass equation, continuity equation, momentum equation, and so on. Yeah. Now we reach to the solver, means you solve or you click the analyze problems, analyze button in the ANSYS. So what happened in the solver stage or solution stage? So there are the flow, the working flow will be start from the method, means equation. Then you will start, then it followed by the input, the parameter input. You change the diameter, you change the loading, you change the speed, and so on. And then the computer will run the algorithm. Okay, so in solver, it will check the equation, it will check your input. If no input, you'll wait for your input, then it will go to a solution. It will calculate for it. Yeah. So later on, you will see the steps in the ANSYS later on. These are the side note. Yeah, this one I think I need to mention, because when you use CFD, when you read CFD textbook, you will come across a name called explicit and implicit. So explicit, implicit is a mathematics algorithm problems or method that used to solve unsteady states. When you have a steady state, the computer will go and choose iterative method. So this one is under advanced mathematics already. Yeah, but today class we just touch and go. Just let you some idea. What kind of category of method used for unsteady state and steady state? So when you have a steady state, then you use iterative method. If not, then you use other two. Yeah, the rest is just, you can read on the screen. What about post-processor? Post-processor is the results. So after you run the simulation or you run the calculation, you will get a certain value from what you input. So when you come to the result presentation, it falls under post-processor stage. Yeah? Then you do evaluation on there's a stage called testing, which is evaluation. You check the accuracy, you check the conversion, the aspect ratio, and all this. Yeah. There are some textbook definition for these two terms. One is called verification, one is called validation. So that's why when it comes to your FIP, we are very careful in the wording that you use in your objective and also in your discussion. So when you use the word verification, how you verify, most of the time the examiner will ask you how you verify your results. Verification itself is that you compare what you get from the simulation, you compare to other people's works, means publish acceptable results. Means it's on paper. How you verify your result means you check your answer or check your results that you get. You compare to journals results. You compare to a thesis results. You compare to a conference presentation, for example. Yeah. So this is called, the process is called verification. So when the examiner or when you publish for a paper, the chief auditor will ask for verification, data verification. So if this part you do not do it properly, then you're not able to publish your paper, or there's a pending answer from your side. Yeah. And then another one is called validation. How you validate your data. the word validation itself is you take your result, what you simulate in the computer software, you compare to the experimental result, mean you go and test it. For example, if you run the simulation on fluid itself, for example, you in the simulation, the fluid velocity that you calculate is 10 meter per second at certain point, certain time. So if you go and set up experiment, you hands-on, you go and collect or go and collect the data, then you do comparison. This process is called validation. Okay, so there is a difference between verification and validation. So verification means you compare with paper, with published data, textbook, and so on, handbook, and so on. How you verify whether you are in the correct direction or correct data. Then validation means you go and validate it with real data. Means you go and conduct experiment, you go and collect from physical simulation. Yeah. So this is these are the differences when you use the term verification and validation. These are the process when we apply CFD. So yeah.
Yeah, sorry to interrupt. So for the verification, right?
Yeah.
So for the verification, we just have to do between the numerical result, is it?
So
Analytical.
yeah. So verification is just on the, for example, you get a set of okay, what final year project you do already?
Okay, I'm doing final project regarding the NC simulation, and then
On
the
what?
verification
On what?
On generator.
Generator, what parameter that you are generating from the software?
Okay, I'm the parameter that I'm generating is I just want to find the temperature outlet of the refrigerant.
Okay, so you're focusing on
To see
temperature.
the
Yeah.
temperature distribution.
Yes. So you're looking at temperature distribution. So
Yeah.
they must be someone that already run the similar results or similar approach that that can help you to double check whether your simulation result is correct or not. So for example, you are running on the temperature distribution on the solar panel, right? So there will be some application, the similar application published by someone. So you go and check whether uh, their input, for example, their surrounding temperature, correct? Their input must be similar to you. So if their input, like for example, density and all these must be matched to your input, then you can do comparison.
So if I do the calculation, once I calculate with the input, if then compare with the simulation, then it must be almost the same, is it?
It might make some sense. For example, other people, he input a certain parameter A, then he get a distribution B, right?
Okay.
So then you also follow input parameter A. Then you come out with a result maybe C. So you compare B and C. So you see what is the difference. How far, what is the gap? This is called verification. It's not verification is not like you have to match 100%. It's just a process where you go and compare with other people. Understand?
Okay, sir. So and then what about the validation? Validation, we have to do the verification and also the validation, is it?
It depends on your scope. It depends on your objective. Yeah, if your objective state the word validation, then you have to conduct experiment.
Okay. Because I'm just doing only the verification.
Then verification. Then stay with the verification. Validation means you have to have a result. One means you have to go and conduct experiment and measurement. There's a measurement there.
Okay, so okay. All right.
Okay. Yeah. So of course there are some examiner they don't differentiate verification and validation, but you can share the definition of verification and validation. You can stand by like textbook definition, what is verification, what is validation. when you try to answer question in your Q&A during your Viva. Yeah. So I mean you can defend your objective, like you are at the verification stage, and your scope is not, for example, your objective do not have validation, then you stay with the objective and you say that validation state may be part of your future research activity. Yeah. So you do not
Okay,
include
sir.
in your what you call, in your part of your presentation. Yeah. So because when you talk about validation, then in your presentation or in your report, you have to mention about methodology, how you set up experiment, and so on. Yeah. Okay. Then this is I think this is the last slides for this lecture. So what happened is CFD means you start initialization and then you go to solution control, means you start for you set for the boundary condition, and then you monitor the solution, means after you click the initiate calculation, you continue to monitor the convergence and all this. Yeah. So CFD calculation, check for convergence. Later on in CFD, you will see this word coming out. I'll show you where to look for. And then if converse, yes, then stop the simulation and continue. Yeah. And see sometimes when you do not meet, do not converge, the software will stop at a certain time or certain iteration. Right? So it will stop there, and then they will come up an error message say that the result do not converge after at what iteration, right? And then you try to modify or improve the calculation. Most of the time you improve on the parameter or the mesh parameter. Okay, all these are the side note lah. So, what else I miss? Yeah. All right. I stop the recording for this one.